Now we'll jump in here and talk about summary parameters. Basically, if you want to measure the properties of a transducer using impedance analysis, what are all of the properties that are needed to take your frequency, impedance, and phase data into something like this, where you have your transducers in a row, your different serial numbers, and you have now summary parameters in your other columns. In your other columns. So you'd be easily able to compare properties, coming up with those summary parameters. So I'll give an overview here, and then in the next slides I will describe each of these in detail. Some of them I've already described before, but I will hash that out to the extent that I didn't cover the information. So the first is the off-resonance capacitance and dielectric loss. I think you're familiar with that from session 1. Next is the resonant frequency. There is capacitance at resonance, which is both important for equivalent circuit analysis and also when you're developing circuits to analyze the equivalent circuit, to analyze your or drive your device. It's an important parameter to know. It also relates to electromechanical coupling, as I'll describe in a couple of bullet points here. The next is the resonance frequency impedance, or you can go with the real admittance. Basically, a summary parameter for that resonant frequency. The next is the resonant frequency real admittance, which is basically also called conductance. Then there's the quality factor, and you can use a quality factor at resonance or anti-resonance. Both are preferable if you can measure and include both. But if you're, for example, primarily focused on your a resonance operated device, then you wouldn't really benefit from using an anti-resonance quality factor measurement. The next is the anti-resonant frequency, and how to determine that, the frequency of maximum impedance. Next is the effective electromechanical coupling factor. It's very true and similar to its name. It relates input energy to converted mechanical. It relates input energy to converted mechanical energy. The other thing to note is the existence of spurious harmonics. This is more on the qualitative analysis of your impedance response. We had described there to be a single resonance and anti-resonant frequency for your operation, but there may be multiple resonance or anti-resonance occurring, and that is due to multiple harmonics or operating modes occurring simultaneously, which can either be due by design, that they theoretically are present. There's two different types of modes operating at a similar frequency, or it's due to geometric tolerances, which can cause multiple modes to occur at slightly offset frequencies, which can significantly disturb the operation of your device. Let's go ahead and describe all those parameters related to resonance. So firstly, we have our resonant frequency, which is defined by the frequency of maximum real admittance, which is also where the power is maximum for a given voltage input, assuming that's constant. So it's that ratio. It's very similar to that ratio. So the way to calculate, if you're going from your impedance analyzer will likely be able to display real admittance or conductance, which are the same thing. But in order to calculate the value from impedance and phase, here's the formula for that. So the real admittance is equal to 1 over the impedance magnitude multiplied by cosine of the phase. So if you say this is a negative, if you say this is the real the impedance phase, technically you have to take the opposite of that for admittance, but because you're using a cosine, it doesn't matter. And this again here is going to have to be in radians. Just note very carefully that real admittance is not equal to 1 over the real impedance. That's due to complex number math, and that's not a process we'll go into in detail here, but just know these are not equal. So once you've found your resonant frequency, the next step, what you could do is to just note your real impedance. Your real admittance. You can also take a look at finding the parallel capacitance. From the imaginary admittance, which is calculated with a similar value, using this formula, 1 over the impedance magnitude multiplied by the sign. And now the sign matters of the negative impedance phase, and that gives you the imaginary admittance. Other things you could do if you wanted to look at the real impedance, so the absolute impedance minimum, you can also look at that and report the absolute impedance minimum too. So these will occur at a different frequency, not at the true resonance, but those are also significant parameters to record if you're trying to get a holistic understanding. The next part is the quality factor at resonance, so let's call that QR. It's also called QM for mechanical quality factor. And that is equal to the maximum real admittance divided by, well, sorry about that. It's not the maximum real admittance, it's the frequency of resonance from admittance divided by delta omega, so the delta frequency, half power bandwidth. So this is where admittance is 1/2. So I'll repeat this. So if we have real admittance, here's the maximum, and there's about 1/2 that maximum. This is the resonant frequency, this distance, and this is the omega. This distance is that delta omega. So taking that half, where the impedance admittance is half, that would be the way to calculate the half power bandwidth, thus giving you your quality factor. You can also use absolute admittance and the peak of that to determine quality factor, or the absolute value of impedance, but this always works. First of all, they're all based off the same theory, but this always works. And there are times when these do not work to use, and you also have to use this. You don't use a half factor; you use a square root of 2 factor. So for admittance, you have to be square root of 2 lower, so 1 over square root of 2, and for impedance, you have to be square root of 2 higher, because as you may remember, impedance has a minimum. So you have to be, this is your impedance minimum, and you have to be z square root of 2, which is about 1.4 times higher. Now I'll describe anti-resonance parameters. And if you just remember again, Anti-resonance is where there's that deconstructive interference, where you have one wave going like that, another wave going like this, and you'll end up with a really small results. If there was no damping, it would be 0, but you end up with really small results at at the anti-resonant frequency. If you had examined an impedance plot, you'll find that, well, the anti-resonance is the maximum impedance, lowest current flow. If you then plot your real impedance, it has a maximum at anti-resonance, and it's going to be slightly lower. Just like the resonant frequency was slightly higher than the resonant frequency, the anti-resonance is going to be slightly lower than its anti-resonance frequency. So that's how to find the anti-resonance. You get that from ZR max. Now ZR max, and so for very high Q devices, ZR and Z absolute are about at the same frequency. And this is also true for the resonance frequency. If the Q is very high, then then there's little difference between the frequencies of real admittance and absolute value of admittance as well. But we want to make sure that we're not trying to leave it up open to interpretation about what the actual value we should be analyzing is. We have to just simply calculate the real admittance. So the real impedance, and that is done using impedance magnitude multiplied by sine of the phase of impedance. And that will allow you to calculate this value. You can also calculate a Q factor using the half power bandwidth, so half of the real admittance. Half that, we look for this delta. You can use your cursors, you can set up an automated function to do it. You can do interpolation if you don't have the exact number of frequency. The other factor that comes into play from the anti-resonant frequency is the coupling factor. In broad terms, the electromechanical coupling factor, denoted as K squared, is equal to the converted energy divided by the input energy. So what this means is that for example, you apply a voltage, and that energy is then converted to strain. So now the piezo holds energy, mechanical energy, from that voltage. If we look at our off-resonance capacitor, the external voltage source applies voltage, and charges are developed according to what it sees from the entire system. That's the input energy. Then the resulting effect is that some of the energy goes into capacitance, intrinsic or static. The rest of it goes into this electromechanical. We've also denoted as C1 at times. So if you want to come up with the ratio, if you want to come up with the ratio between the converted and input energy here, the converted energy would be following this equation there. Capacitance EM divided by, you could put this 1/2 CV squared there. 1/2 CO plus CEM V squared. The voltages in the 1/2 will just drop out. So you'll end up with the electromechanical capacitance divided by the total capacitance. And I'm just going to call that C for now. So this is the electromechanical coupling factor. And when we spoke about this LCR circuit, well, analyzing these capacitors alone, assuming they're analyzing these capacitors and not necessarily considering the resonance phenomenon and amplification of energy or increased storage of energy, but looking at things more on a cycle per cycle basis, we can also use C1 over C0 plus C1. So this is the input energy, this is the converted energy, and you can look at that information per cycle. And this is the effective electromechanical coupling factor as calculated from the equivalent circuit. Now you may ask why this is called effective, and it's called effective because it's not based off of material constants. It's a more transducer and also resonance based resonant strain and stress distribution phenomenon. So this is also called K effective for that reason. So then in order to just get the coupling factor in its common way it's represented without the square, you'd have to take the square root of both sides. Then you just end up with K effective. Now there's yet still another way to calculate this, and the equivalent circuit's not the standard way, although it's a very acceptable method. As you're kind of finding, you're able to get two parameters in different ways, but the important thing is that you provide enough parameters that you can calculate the other ones. And the other important thing is to note how you did that calculation. So the other way to calculate the electromechanical coupling factor, and it's quite unique here, it's equal to 1 minus the ratio between the resonant frequency and the anti-resonant frequency squared. This can be derived from the equivalent circuit, which has a resonance and anti-resonant frequency. So this can be derived from this, but now we don't have to do an equivalent circuit calculation in order to determine the coupling factor. We don't have to do an equivalent circuit calculation in order to determine the coupling factor. We can directly take measurements of the anti-resonance and resonant frequency to do that calculation of the coupling factor. And again, the way we represent it typically is just with the coupling factor not being squared. So we take this and that's our coupling factor. Now you'll note that this relationship still holds, that the coupling factor squared is equal to C1 divided by C0 plus C1, and that now is equal to 1 minus omega r squared divided by omega a squared. So this is another equation you could actually use in order to determine your equivalent circuit. So you just need to have 4 unique values, and you'll be off to the races. So you don't technically, the Q measurement you don't have to do. The QR, you don't have to do the QR. So for example, from your resonant frequency, you can extract capacitance, you can extract the resistance. R1. From your resonant frequency as well, you can determine LC. So the combination of L1 times C1. So from your coupling factor, which comes from your anti-resonant frequency, you can determine C1. And from these two, C1 because this equation, you already have CO or C0 or C0, therefore you can calculate C1. And from this, you can calculate L1. So there's another way, without measuring the quality factor, that you can get to the results. It'll be likely to fit the resonance and anti-resonance features better. It's more appetizing to look at it, but it will be more accurate for you to use quality factor because you are using only resonance calculations. The more parameters you can extract in a smaller frequency range, the better it's going to be. Because you could also include off resonance capacitance here and do calculations as well. So instead of off resonance, so F, I'll call it omega O. So that's off resonance. That will just give you C, and we do know C is equal to C0 plus C1. So you don't. Let's say you're. Let's say this happens where you're off resonance. And this is a very interesting result where your C0, your resonance capacitance is very small, and you're not able to measure it very accurately. So let's ignore that. So we can then use. You don't have to use that part. You can use the off resonance capacitance then to determine. Use your off resonance capacitance in conjunction with your coupling factor to determine C1, and then you'll be able to determine CO. Then you'll be able to complete the rest of the calculations. So there's multiple ways of going about calculating the equivalent circuit parameters, using a few parameters to measure the others. I would personally not rely on that format. So like, oh, I don't need to measure, keeping my anti-resonant frequency because I already did my resonance Q, and you can, as long as you get an equivalent circuit, you can then calculate an anti-resonant frequency. Well, that's true, but it's better due to sometimes the device not being consistent with linear theory. Surprise, surprise. Not everything in life is linear. And sometimes the deviation is larger, sometimes the deviation is smaller, but that's the way things work. So in that case, I would just measure all of the parameters such that you can calculate the coupling factor in many different, in all the parameters in many ways. You don't need to rely on any certain method in case there are errors. You have those original parameters. The other thing to be aware of when you're doing your impedance analysis is what's called the existence of spurious harmonics. These are a little bit different from just other harmonics in your system that we'll speak about. But what these spurious harmonics look like, if you have let's just use impedance, magnitude, and frequency. We'll also draw a phase down here. Let this be a zero phase. So say you typically have a device that looks like this. What spurious harmonics would look like is if you had multiple peaks here, and then you'd come at your anti-resonance, and you'd have sort of jagged behavior. These are spurious harmonics. The first cause of them is, well, if you have an assembly, let's talk about an assembly. Is geometric tolerances. So you have slight mismatch. Let's say you have a circle, you have a disc and you have a piezo bonded to it. The mismatch in those geometrical tolerances. Then there's also assembly defects, like there's better bonding in one area versus another. The third is uh, underlying other underlying modes. For example, you have a device where you have bending motion, but you also have other harmonics which are pure axial motion at similar frequencies. They just happen to be at similar frequencies. Those can cause underlying modes, as well as other components, other components in resonance in your device. And we'll actually speak about that. I'll actually talk about it in a few slides here. But usually the ones that we really worry about in terms of the build quality, because these can be designed a way in FEA you can use. You can do a DOE with geometry. The assembly defects and geometrical tolerances are harder to capture and monitor. They may be more sensitive for a particular design of a device that may be more sensitive, and you don't know about these modes until you actually build your device. Hence, it's important not to stay in your finite element realm for too long. So what will actually happen? So if you have a device, even two devices without spurious modes, let's say this is the first one, no spurious modes. And then we have another one with spurious mode. Typically what happens is that the coupling becomes worse. Like the impedance is higher. That also consequently means a lower real admittance. You wondering where is the resonant frequency here? That's another question that comes up at this point. And the phase also, we haven't used phase extensively yet, but the phase also becomes more, also shows the spurious nature. Instead of smoothly transitioning from negative 90 to 90 and back to negative 90 degrees when the piezo becomes capacitive again, you have more jagged and irregular behavior, which are related to those other resonant modes. So noting this is important. There are ways to get more analytical about what these modes are and their strength, but I think initially just noting their existence is important. So here we'll analyze a piezo buzzer with some spurious mode behavior. And I'm going to go ahead and plot the real the impedance magnitude and the phase magnitude. And we'll put it in logarithmic form. So the blue is impedance. So we have our impedance decreasing as we expect. Then it's coming back for an antiresonance, and there's a second resonant mode right there. Bending mode actuators are especially susceptible to this, but when this happens in a longitudinal mode actuator, like an ultrasonic cleaner, bolt clamp device, this is a big reason for concern. But we'd prefer this not to happen in our bender transverse piezo device, but it does happen. So it's important to note that this occurs, and also save the data if you see if you can look for a trend. If you look at the red, the phase, it also shows a very significant deviation from just going from 90 degrees back to negative 90 approximately. I'd also like now to look at real admittance and real impedance. We'll check them out on the linear side. So this is really interesting. So we have in blue our real impedance, real admittance. In the higher it goes, the higher power for a given voltage. So we have maximum. We also have this sort of bump here too. It's interesting to note. We have maximum, we come back down, and we also have our pair real impedance. And we come back down and we find another resonant mode right there. So this is clearly would enable to, if you were to look at impedance before, if you remember what that plot looked like, I'll show it again in a second. You wouldn't be able to pick out your resonance and anti-resonance frequencies, but here you can actually clearly tell that there's a mode there, there's a mode there, and again now there's a mode here. This is the resonant mode of this frequency. So right now I have the cursors automatically set to the maximum real admittance and the maximum real impedance. But if we wanted to shorten this up, so to go from 42 kilohertz to 4.4 kilohertz, I'm going to change the scale, 4.4 kilohertz. Let's just run that again, and let's let it. There we go. So this is the resonant response there, and we have a resonance and anti-resonance picked out. So that's a little bit about spurious harmonics, their existence. Sometimes you'll still be able to make your measurement with them there, sometimes you won't. But a curious point is actually if you just looked at your resonance, if we did the original method for calculating the equivalent circuit that I taught, if you do that, you can actually do that, and even if there's a spurious harmonics at anti-resonance, you can still do that. You use all the parameters at resonance, and ignoring anti-resonance, you can actually still calculate a coupling factor if necessary. So you sort of look for the most ideal way of calculating the parameters in a way that's meaningful to you and your goals. So I'll exit that. In this slide, I will describe the difference between transducer and material analysis. So a transducer is a general term for any assembly or piezoelectric material. However, and this could include, your ultrasonic cleaner. It could be a ultrasonic welding device. It could be an ultrasonic surgical device. It could be a humidifier. It could be a piezo bender. And material analysis, what we mean by that is a simple resonator. With only piezo material. It's a simple resonator with only piezoelectric material. So what this looks, I'll describe what it looks like and why we would want to do this for characterization. So if we have a piezoelectric plate, it's the longest direction is the length or the width in this case in a single direction, and the other two directions, the thickness and the width are small. in this case, we have if we stimulate our piezoelectric material, we'll have the resonant frequency will be the longitudinal resonance across the length. This will be the first resonance frequency. From this resonant frequency, it's going to be theoretically related to the compliance in that direction. It's called a 1-1 direction. So it's going to be related to a material property. And not only related, it will have a closed form solution relating the natural frequency measured, through the minimum impedance to your material property. So by using simple geometry such as a bar, which is uh, which is long in the width direction, or if you use a thin plate, a circular plate which has what we call radial vibration, or if you use a bar which is longer, and the top and bottom are the electroded portions here. If you use a long bar, it will have resonance in this length direction, which corresponds to the compliance or the stiffness in the thickness direction. Well, it's actually the semantics are that it's a constant electric displacement, but we'll leave that aside. It basically relates to a condition which describes a material property in closed form. Now, if you look at a transducer, let's just take a piezoelectric bender, which has the piezo material on top and another passive material on bottom, and when it's excited, there's bending motion. The resonant frequencies here will not have a closed form solution relating to the different material properties, such as the piezoelectric charge coefficient or the piezoelectric stiffness or the compliance. At the same time, as well, in these cases, you'll find one other aspect. And the other aspect that you'll find is for the coupling factor. The other aspect that you'll find is that the coupling factor, K, effective, well, it's no longer effective for the simple piezoelectric plate and its determination. But it's also a lot more complicated. It's also not 1 minus the resonant frequency divided by the anti-resonant frequency squared. It's also not this simple relationship anymore. The reason is because there is a stress distribution. So if you just take a piezoelectric bar, and I'll just draw it in 2D, and it's resonating, we have a stress distribution, and it's zero stress at the boundaries. Stress. And in order to determine the material property, and if you look at material properties, they don't, if you apply them infinitesimally or, to a infinitely small portion and you do that level of theory, then you will have basically constant stress. If you look at a very small area or a very small region, you have constant stress over that region, and that's how you define your material properties. For example, the very common relationship stress and strain. And this is strain, and that equals stress. So these relationships, in order to extrapolate this curvature into a material property, which is a coupling factor, is a material property. In order to do that, there are more complex. There are more complex representations of the coupling factor and the relationship between the resonance and anti-resonance. The relationship will be more complex. They'll have some extra sinusoidal functions here. They may have the Bessel function relating other parameters. It's not as simple as just 1 minus the resonant frequency divided by the anti-resonant frequency squared equals the coupling factor. You can still calculate an effective coupling factor, but you wouldn't get the coupling factor by which you can relate material properties. And the general form, after you extract using the appropriate formula, which can be derived for a specific resonant mode, for example, in this longitudinal bar, you will have the, assuming polarization in the thickness direction and driving up top and bottom electrodes, you'll have a coupling factor coming from this, known as a K31, which is the electric field applied in the three direction, displacement in the one direction. So that's the Poisson's ratio that working at play there, equals the D31 squared divided by the permittivity and the compliance, which is the inverse of stiffness here. So you have the coupling factors directly related to material properties. In order to do this in a smooth fashion, there is a conversion that happens that takes this distributed stress and makes it compatible with a closed form solution of material properties. So those are the differences. So when you don't apply basically this effective coupling factor to a piezo resonator, a simple piezo, and expect to use a simple formula like this. There are more complex formulas. They are derived. Um, we're not going to go over them here in this presentation. We're focusing on general transducer analysis, but I wanted to point out that difference because you may see different equations for the coupling factor. Those are specific to a resonant mode in order to determine a material property. Uh, but for our analysis, when we're looking at transducers in general, we look at the effective coupling factor for that mode of operation. Uh, which again, it's going to be related to the material properties, but it's not a close form relationship that you can just pull that right out.